Here, I'm going to demonstrate the use of weak law of large numbers for such an estimation. In fact, we are going to do nothing but apply Chebyshev's inequality. Okay, that's the key point. The question is to estimate the probability of an event A, P of a sequence of Bernoulli trials are performed. So you just repeat your random experiment. Why is it Bernoulli? Because the outcomes are what the outcomes you are interested in. Event A occurred, event A didn't occur. Event A occurred, event A didn't occur. That's the definition of a Bernoulli trial. Okay. The question is, how many experiments do I need to have 95% probability that my estimate is going to be within 1% of the true probability of event A? Okay, this is a very significant question in applications because, well, for instance, you are running a simulation and you would like to know when to stop it. If you let it run too long, well, as the name suggests, it's too long. You don't wait too. You don't want to wait too much. But if you run it too short, then your result may not be precise enough. Okay, so what is the sufficient number of trials that I can estimate this quantity? Now, here I'm going to define these Bernoulli trials as x by 1 or success if event A occurs, 0 if it doesn't in experiment number I. Okay, now we know that the probability of this outcome is P in reality, right? But we do not know the value of P. Incidentally, the mean of a Bernoulli random variable, which is x sub I here, is also equal to its parameter x, P. And also we know that the variance is equal to P times 1 minus P. The problem is we do not know the value of P. So what we do is we just observe that this variance, P times 1 minus P, is upper bounded by 1 over 4. In fact, if you plot this function, right, because P is a probability, it will take values between 0 and 1. It's a parabola, P minus P squared. It's a parabola in this form, okay? And its peak value occurs at 1/2, which happens to be 1 over 4. So for all other values of P, P times 1 minus P is below 1 over 4. So this is a key observation. And obviously, we define the probability estimate of event A as the sample mean of x sub i's, okay, 1 over n times the sum of x sub i's from 1 to n. And the probability, the variance of this probability estimate, as we have derived before, will be equal to the variance of x divided by n, because x sub i's are IID. Okay, so just apply Chebyshev's inequality to this probability estimate. The probability that this probability estimate is within epsilon, or, well, since I have greater than or equal to here, is not within epsilon of the true value P, is upper bounded by the variance of the probability estimate, or the sample mean, divided by epsilon squared. This is nothing but Chebyshev's inequality, okay? This part is just Chebyshev's inequality. You have to see the application of Chebyshev's inequality here. And this variance, as we have established here, it's variance of x divided by n. So this expression is equal to variance of x divided by n epsilon squared. And variance of x is equal to P times 1 minus P. And we don't know the real value of P times 1 minus P, but what we know is it's upper bounded by 1 over 4. Okay, so if I put 1 over 4 instead of this, my expression will also increase. Okay, so I can do this because this probability is less than or equal to this value, and this will be less than or equal to this. Just instead of this, if you write 1 over 4, right, what you get will be a larger value. So this expression is smaller than this expression. 1 over 4 and epsilon squared. Now, what I have found is this probability is upper bounded by this quantity here. But why I'm interested is the complement event of this. The probability that my probability estimate is within epsilon of p. So it's the complement event, which means it's 1 minus 0.95. And since I'm taking the complement, this inequality will change direction. This is greater than or equal to um, this quantity, okay? And that is 1 over 4 times n times epsilon squared. If you plug in the epsilon value, which is given in the question as 0.01, and arrange the terms, you get n greater than or equal to 50,000. So what does this tell us? To ascertain and estimate for the probability of an event A through repeated independent experiments, okay, if you perform at least 50,000 experiments, you will be guaranteed to have your estimate within 0.01 of the true probability with 95% probability.